Hello everyone, welcome to Saturday Night SQL Virtual Group. My name is Sarah Huang. I'm the founder and organizer of this virtual group. Join me here is Debbie Huang, our co-organizer. Today, Andy Yuan will present why your data type choices matter. This is a very good topic and was presented at a past summit 2016 by Andy. Andy Yuan has about 15 years of experience in database development and administration. He speaks at various events such as SQL Saturdays and past summit. He's also a leader of multiple user groups. We really appreciate Andy took the time to share his knowledge with us today.
Hello, everyone.
Hey, this is Andy. Let me first go through a few slides regarding the PaaS community, then I'll transfer the screen over to Andy. As you may know already, PaaS has been working on launching its new brand and website. In addition to the changes of the brand and the website, we also PaaS will also be adopting new names for local chapters and local virtual chapters, and basically just replace chapters with the groups. So this the changes will be rolling out to the community in the next few weeks. PaaS e-store is gonna close soon, so if you would like to order the soon retired brand named merchants, please go to the website. And there are some virtual chapter meetings left for the remainder of the month, like DB fundamentals and women in technology and that. Regarding to our future virtual group meetings, in March, Steve Wick will present reports on the Go SSRS 2016 mobile reporting. And in April, Haidongji will present initial impressions of SQL Server v.next public preview. And in May, Barbara will present Power BI 0 to dashboard in an hour. And in June, Steve will come back and present SSRS 2016 reporting. PaaS has many virtual chapters. You may choose to join one or multiple. The membership is completely free. Of course, you're more than welcome to join our virtual chapter or virtual group, if you will, which is Saturday Night SQL. Sorry. There's some SQL Saturdays events going on in February and through March. You may want to visit SQLSaturdays.com for more detailed information. And PaaS is pretty much mostly run by volunteers. And if you would like to volunteer, please visit volunteer.sqlpaas.org for local opportunities. And if you are not a member, please join SQL PaaS. The membership is completely free. If you would like to ask questions during our webinar, there are two ways to do it. First, you can, if you would like to ask Andy questions directly, you may raise your hand. Use this little hand by click this little hand button. Then we can unmute you, and so you can interact with Andy directly. Otherwise, you can type your questions in this chat window. We will read the questions out loud for you. Okay, let me transfer the screen over to Andy. Andy, thank you so much for present for our community for our virtual chapter.
Hey, you're most welcome, and thank you all for joining me tonight. I'm super excited to be here. Give me a moment. Let's see, I just want to make sure that everything is showing properly.
Yeah, I can see your screen now.
Okay, very good. One other thing I just want to double check. I'm trying to see where I can use my webcam, but that option does not seem to be available. That's
Can,
interesting.
can you see there's a little camera on the right hand side on the top?
I don't
I
believe I
can.
have that option right now. You may have to actually make me an organizer um,
Oh,
rather than a
okay.
panelist. So yes, make me an promote me to organizer, and then I should be able to use my webcam.
Sure. Can you see it now?
Let's see, one, two.
From my end, I can see it on the top, on the right side. I think for a second, I think I saw your picture.
No, that was me actually accidentally
Oh,
advancing the slides. I'm going to give
oh,
this another
okay.
10 seconds. If I can't find it, we're just going to move on. So, and not spend any more time on this. All right, forget it. Let's get started. So thank you all for joining me tonight. This is my presentation from Past Summit 2016 of why your data type choices matter. Every byte counts. Slides. There we go. My name is Andy Yoon. I am a senior SQL Server DBA with a company called Insona. We are a managed services company. Here's a little bit of information about me. I run a user group. I help run Chicago SQL Saturday. I present at various events. I'm actually super excited to be presenting in 2 months at SQL Bits. If you're not familiar with SQL Bits, it's the largest SQL Server conference in Europe. So I'll be traveling to England for that. I'm super, super excited for that. One other important thing that I always like to point out on this particular slide is that not only am I an operational DBA now, I'm also a database developer. And in fact, I've spent the majority of my career as a database developer. And the thing is, the reason I like to point that out is that because sometimes during some of my presentations, it may sound like I kind of dig on developers a little bit, but here's the thing, I'm one of you. I've spent the majority of my career as one of you. And there's been many times in my career where I've made a lot of the same mistakes. So don't feel bad if it sounds like I'm digging on devs, because I am one of you. But here's the thing. Being both a dev and a DBA, I've been able to build bridges, if you will, between the two camps, because oftentimes operations and development are at odds with one another. So a lot of my experience being on both sides of the fence has helped build a lot of bridges and bring those worlds together. So with that, let's dive right on in. All right, data types. Who chose what? So when was the last time you took a look at a brand new database? Maybe you started a new job. Maybe you brought in a new vendor application. Maybe your development team just threw over a new database that you said, hey, we're rolling this out, take a look. And you looked around at the tables and the table definitions and the data types, and you your gut told you that this isn't right. Now, sure, an address could be stored in nvarchar max, a zip code could be stored in an integer, but for whatever reason, this just didn't sit right with you. Or how many times has someone come up to you and asked you, why can't we just use nvarchar 255 or, big int everywhere? Why can't we just use these data types everywhere? What's the big deal, right? Well, hopefully after the next hour and 15 minutes together, I'm going to be able to arm you with not only just general knowledge as to why, but some really solid technical knowledge as to why these data types are not a great idea and why your data type choices really do matter. I find that data types are often one of those topics that it's very fundamental, but it's also one that gets overlooked a lot, because the thing is, a lot of people just don't pay it much attention, even though they really should be. And hopefully after the time we spend together, you will have a better appreciation of why. Just so you know, this is technically a 200 level session, but when I was accepted to present this for Past Summit, I had to up my game. So you're going to actually get a decent helping of 400 level content in here as well. But not to worry. I tried to set this session up such that there's something for everyone, if you will, beginner, intermediate, and advanced. And we're going to dive into the 400 level content right now. SQL Server internals, how data is stored. Now here's the thing, don't be afraid of internals. I'm a strong believer that all of us as SQL Server practitioners should at least have exposure to and a basic working knowledge of SQL Server internals. You don't need to be a guru of internals, but just like a car mechanic learns the ins and outs of an engine just so they can squeeze some extra horsepower out of the engine by tuning their engine, we as SQL Server practitioners, if we want to be performance junkies, like I like to think of myself as, then we need to learn some internals so that we can squeeze more horsepower, better performance out of our SQL servers. So for the purposes of our discussion today, we're going to be using this employee table. Now, rules of the game. Let's pretend that this employee table is for an application for a US-based company, okay? So looking through this employee table, we store a lot of typical data points that you would find, for a company's employees, name, gender, social security number. We have some breadcrumb columns down here, like the record created date, last modified by date, et cetera, et cetera. Now, the first rhetorical question I kind of want to throw out to you guys is this. Do you think that SQL Server cares about the order of which you have defined your table columns? Meaning, or to put it another way, when you create this table, do you think that SQL Server will actually physically create your table with the columns in the order that you have defined them here in your code? The answer to that is no. What happens is that SQL Server will use something called the fixed var format, where fixed with data types come first and variable with data types come second. But which are fixed and which are variable? So long ago, when I first started in my career, I never really thought about fixed versus variable length data types. It's not something that most people really consider. And to be perfectly honest, I didn't even look at what these data types were. And when I was really learning about this, I was really surprised that there's actually a lot of fixed width data types out there. But Andy, what do you mean by fixed width data types? What I mean is this. Say, for example, an integer is a fixed width data type. Regardless of the value that you store within that int, it will consume the same amount of storage space. So if that int is storing the value 0, if it's storing the value 1,000, if it's storing the value 1,000,000, if it is null, then it will still consume the same amount of storage no matter what, as opposed to a variable with data type. Well, how much storage? Let's take a look. So here's a breakdown of some of the more common data types, again, the same ones that we saw on the slide before, and the amount of storage that they require. So an integer requires 4 bytes, a big int, on the other hand, requires twice as much at 8 bytes. A couple of things I'd like to point out. Ooh, sorry. Wrong keys would zoom it here. I'm trying to use the drawing tool. Where'd you go? Ah, there we go. Okay, so the couple things I wanted to point out is that we have char and varchar versus nchar and nvarchar, right? Notice that with the n data types, the storage requirement is n times 2. What do we mean by that? What's going on here? Well, the n data types support Unicode, and Unicode allows us to be able to store data that does not fall within the typical ASCII character set, such as, say, Chinese characters or Russian characters or other foreign languages that don't fall into what we typically see in the English or ASCII character set. So if your application, you need to support that, you need to use either nchar and varchar. The consequence is that if you're doing, say, an nchar 10, then that requires 20 bytes of storage, twice as much storage as opposed to char or varchar. The other interesting thing that I'd like to point out is notice that with the two variable with data types, there's an extra 2 bytes of overhead. So the interesting thing to think about there is that if you're storing something that's very, very short, and it's always going to be very short, from a pure storage perspective, you may be better off with, say, a char1 as opposed to a varchar1, which will require 2 or 3 bytes, as opposed to a char1, which will only require 1 byte of storage. What those 2 bytes are, we'll get to shortly. So hold that thought. So let's take a look at the actual fixed var format. What we see here is the breakdown or a definition of an actual record. The first 2 bytes of the fixed var format are status bits. It holds some metadata information about that record. The second is the total fixed length size of the record, of the fixed length data types, that is. The F data is the actual fixed length data. Then we have the total number of columns that are presented in the record itself. And then we have something really interesting called the null bitmap. Every single column in your table, regardless of whether it is nullable or non-nullable, will have 1 bit in the null bitmap to represent it. And SQL Server uses the null bitmap to tell or to denote whether that particular record and data column is null or not. You can't actually store null in either the fixed data or the variable with data because null is not a value. Remember, null is a state of being undefined. So it's not the equivalent of empty string or 0. Null is just null. We don't know what it is. It's completely undefined. So if your table only has fixed width data types, we stop here. But if you happen to have variable with data types, then we will continue. We'll use the var count, which will show the total number of variable length columns. We will have something called the variable column offset array. Remember that extra 2 bytes of overhead? That's what's represented here, because that offset array are essentially pointers to the actual variable with length data. Let's take a closer look at an example of the fixed width data and then of the variable with data, and I'll break it down to kind of show you how this all works. So pretend we have these 5 fixed width columns, and these are the particular data types here. So we know what the total size is 144 bytes. So say, for example, if we want to get the social security number, SQL Server already knows that it just needs to jump 20 bytes from that point in the record in order to start reading the social security number, which is 100 bytes, because all of these fixed width data types, fixed width columns, their sizes are set. They're never going to change. Even if employee ID is null, if gender is null, it doesn't matter. Variable with data types, on the other hand, are a little bit more interesting because now we have this variable offset. We don't know exactly where the first record will end and the second record will begin. So we have to use this offset. They're essentially an array of pointers, and that's where each variable with column has an extra 2 bytes of overhead in the variable offset here. So if you follow the simple arrows, if we wanted to pull title, we have to jump here. Or if we wanted to pull email address, we do the jump that way by looking at that offset, and that offset is a hex address that will actually point us to where the actual value begins. Okay, so let's take a look at employee large again. Now, taking some of the things that we just learned, we can derive a few interesting bits of information. The one bit of information for the purposes of our discussion today is that we can figure out that at best, or at minimum, how much storage will one single record of employee large require? Because the thing is, remember, for every single fixed width data type, regardless, even if they're null, it's going to require a small amount of storage. And in this case, 1,300 bytes per record. That doesn't sound like a lot, but here's the thing. I argue we can do better. We can do much better. How? By right-sizing our data types. What do I mean by right-sizing? Well, let's take a look at some of these different data types and the values that they support. If, for example, we have the date hired is a date time, but the thing is when we store date hired, we don't care about the time that you were hired. It's just going to be set to midnight. So really, we can just change that data type to a date instead of a date time, and we've just saved 5 bytes. We've saved over 50% or reduced our storage requirement by over 50%. And keep in mind that even though this is just a few bytes, these bytes add up. Don't think of this in the context of one record. Think of this in the context of a table with millions of records and dozens and dozens and dozens of tables. All these bytes add up fast. So let's do a right-sizing example together, a little bit of an exercise. Social Security number is currently defined as an nchar 50. Think to yourself, would you use a date, a number, or a string? Well, I would use a string of some sort. Now think to yourself, would you use a char, an nchar, a varchar, or an nvarchar? Well, remember, I said the rules of the game earlier, the rules of our application is that we are a US-based company. So I would ask, does our application add the dashes for us? Yes, it does. Oh, in that case, we can use a char 9. But if for whatever reason our application or front end did not add the dashes for us, we may have to use a char 11. And or if we had to actually support other countries, and become internationalized, we may want to change this to something else. But for our application, for the rules that I laid out, a char 9 is just fine. Vacation days remaining, we'll do a second example. If you happen to work for a company where you can accumulate over 2 billion vacation days remaining and fill up that int, I want to work for you. Anyway, so what do you think we should use? A date, a number, or a string? Well, I say that we use a number, but should we use a tiny int, a small int, or a decimal? So if this was a live interactive type thing, or if we were all together, not in a virtual webinar, I would probably be hearing all 3 of these answers. So someone might say tiny int. Well, here's the question. Do you happen to work at a company where maybe you get allocated 2 weeks of vacation a year and you accrue it over the course of the year, but you can actually take those 2 weeks of vacation earlier in the year, therefore you go into the negative? If that's the case, you cannot use tiny int because tiny int only goes from 0 to 255. Now what about small int? Small int can go into the negative, so that may be perfect for you. But here's the thing. In my case, I happen to work for a company where I accrue 1.667 days of PTO per pay period. So therefore, my company, I could not use a small int because of the decimal values by which we accrue. I would have to use a decimal of some sort. The whole point of this exercise is to show to you that you need to ask yourself business questions, ask yourself application questions. Right-sizing is all about not just guessing, but also figuring out what does my business need, what is appropriate for my application, how is my data going to be used. All right. So now that we've discussed the concept of right-sizing, let's go back to our employee table, and I've made some adjustments to it. I've created employee narrow. I've changed around a number of different things and changed all the different data types, right? So what do you think is the minimum amount of storage required for employee narrow? 104 bytes. Do you guys remember what employee large was? 1,300 bytes. We've made an improvement of over a factor of 10. How many people want to tell their boss or say their storage admin that, hey, I just reduced my storage requirement by a factor of 10? They're going to be pretty happy with you, all because you chose a different data type or a different set of data types. So now that we've discussed records, how do you think that these records are actually stored on disk? Do you think that SQL Server just throws these records out there willy-nilly, just writes them all randomly to disk? The answer to that, of course, is no. SQL Server uses another construct, another container, if you will, called pages. data pages. We're going to explore that next. So this is an overview of data pages. There are many other kind of pages within SQL Server, but for the context of our discussion today, we're only going to talk about data pages. And there are three types of data pages: in-row data pages, row overflow, and lob data. 98% of the time, you're only going to be dealing with in-row data pages. All pages have a fixed width size of 8 kilobytes. This is something that was set back in the Stone Ages, and as far as I know, will never ever change within the SQL Server storage engine. And all pages are comprised of 3 different components. First, we have the page header, which is 96 bytes. Those are 96 bytes of storage that's completely lost to you. You can't utilize any of that. SQL Server stores a bunch of metadata within the page header. The B section is where the data records all get thrown into, and then the C section is the record or the slot array. There's an additional 2 bytes of overhead here, because what this is that this is a pointer back to the actual record where it happens to live on the data page itself. The interesting thing about the record and slot array is that if these data pages are part of a clustered index or an index of any sort, where ordering is enforced, the ordering is actually enforced here in the record or slot array. The records on the data page themselves are not actually ordered. They're only ordered in the record or slot array. So that's an interesting little bit of trivia. So I want to focus a little bit on the 8 kilobyte limit. A lot of people don't fully appreciate that SQL Server does all its I/O, it does all its querying work not by records, but by pages. So think of a page perhaps like a box. So if you had to go across the room and return, 5 widgets to me, but across the room you only have boxes and you can only bring boxes back. Do I want to bring back 10 boxes or just 1 box? As such, if we make good data type choices, we can shove more records into pages such that we can have SQL Server do less I/O, less work, pull back less data pages to fulfill our queries. As I said earlier, typically data is stored in row. What if we have things like a varchar max or n varchar? Because here's the thing, a record cannot, in of itself, cannot span more than 1 data page. It will be split up, if you will, if we run into one of these interesting examples. So what happens here? Let's take a quick look. So let's pretend we just have these 2 data types. One is a varchar 8000, one is a varchar max. And the 2 values are just short string and second short string. So SQL Server will attempt to store this in row. And in this particular case, they're both short enough to be able to be stored in row. We run an update statement, and we update column 1 and column 2 to some kind of insanely long string that's thousands and thousands of bytes, much larger than the 8000 max we have. So what do you think happens? Well, SQL Server will replace the values and instead replace them with pointers, and will now allocate new data pages, either row overflow or lob data pages, and then store the values there. And then those values can be stored and concatenated across multiple row overflow or lob data pages with multiple pointers if necessary. So going back to what we were talking about with the minimum amount of storage required for a given record, we can, if nothing, we can come up with and do some calculations and figure out how many records per page can we store at best because of the minimum record size. So for in the case of employee large, at best, we can only store 6 records per page. And yes, there will be some wasted bytes, but there's always going to be some wasted bytes no matter what. Employee narrow, on the other hand, can store a whopping 77 records per page. That's fantastic. That's a huge improvement. Think of it this way. If I have to pull back, again, X number of records, I don't have to pull back nearly as many data pages. Let's look at this from why do we care? Here's the visual example of the point that I just made. So I'm just doing this simple query against employee narrow. I only have to pull back 3 data pages. If I do that same exact query against employee large, I got to pull back a heck of a lot more data pages, a lot more work that I have to do just to fulfill that same query. Here's the difference in numbers. Some people like to see numbers, so I like to show this aspect too. So again, don't think of this as 1 record or 2 records, because we deal with tables and millions of records. right? So if you have 1.5 million records in this particular table, that's a difference of 2 gigs versus 155 megs. That's a tremendous difference. You know, if you have a terrible query that has to table scan everything, that's how much data you have to process through. So with that, we're going to dive into some demo, and we're going to explore records and pages and go through a bunch of really cool stuff that we have just been talking about for the last however long. Let's see now. Oops. Here we go. All right, so I have a demo database called Every Byte Counts. Switch to using that. So first we're going to just take a quick look inside our 2 example tables. I'm just going to do a quick select star, top 1000 select star from employee large and employee narrow. I'm going to order them just to show you guys that both of these tables have effectively the same data inside. Now, some things are a little bit different because, for example, I'm not using GUIDs, I'm using auto-incrementing integers, but otherwise it's the same exact data. Same names, same social security numbers, et cetera, et cetera. And both of these tables happen to have 250,000 records each. Okay? Now, there's a nice way that we can actually get some quick reference and detailed information about each of these tables. SQL Server has something built in, a store procedure built in called SP help. If I run SP help against employee large and employee narrow, we can see that there's multiple tables that are returned for each of these. So at quick glance, I can actually quickly see, oh, hey, here's all the different columns. Here's all the different data types. Here's the lengths of them. Mind you, the length is the data length. So in the case of nchar, this is really a 255, but the length, because it's n times 2, is 510. If we happen to have any, let's see, scrolling down a little bit, happens to live on the primary file group, we have a cluster index here on employee ID, and we have a constraint, which is the primary key constraint. Here's the output of employee narrow. Let's take a quick glance at that. We have, again, different data types being used here. Varchar 100, length of 100 because it's a varchar, not an nvarchar. That's actually accurate here. It's not doubled. We have an identity column on employee ID, so you see that materialized here. Clustered key and a primary key constraint. So this is a really cool built-in store procedure that I always like to highlight. But here's the thing. Typing out exec sp help is kind of a pain, and I'm lazy, and I don't like doing that. So you know what? Management Studio has some really cool features built in to allow you to use keyboard shortcuts. What do I mean? If you go up to Tools, Options, Keyboard, and Query Shortcuts, let's zoom in here. So SQL Server has these 3 query shortcuts built in and hard-coded in. And then I like to use the control keys, so I've actually modified and used control 3 and control 4 for SP help and SP help text. Well, what does that allow me to do? Well, using this, I can now just go through my code, highlight a given table, hit my keyboard shortcut, and bang, I've just executed SP help. So now this information is at my fingertips. I don't have to, so if you, for example, are reading through someone's store procedure, you're reading through some code, or even if you're just writing some code and you're like, hey, I don't exactly remember what that data type is, bang, you can quickly check it just by using this keyboard shortcut. This is something I use all the time. Keyboard shortcut, here's my little note for that. All right, so the next thing I want to show you guys is a DMV called sysdmdb index physical stats. So I'm a big fan of the DMVs. They show you all sorts of really awesome internal information about SQL Server. And in this particular case, we're going to be looking at sysdmdb index physical stats, which will show us some interesting physical information about our different tables. So in this particular case, you have to pass in the database ID, the object ID, and a few other parameters. I'm not going to go into great detail of how you use this. So we're going to run this against employee large, and then we're also going to run it against employee narrow. Okay? So now that we can see the output of this, and this, I've limited some of the output to only the data points that are interest to us today. Uh, Record count, quarter million. The number of pages, 41,000 pages versus just under 4,400 pages, just because of our different data types. You remember how I showed you the minimum record size earlier? I didn't actually do that math. I just looked it up in the DMV because I'm lazy that way. The last data point that I want to show you guys is average record size in bytes. So what I love about this DMV and this particular data point is that it will actually go through your table and figure out this average for you. So you can take a look at this value and then compare it against your minimum and maximum just to get an idea of, hey, wait a minute, my min and my max versus my average could be way out of whack. And that could tell me or be a symptom perhaps of, hey, maybe I should take a closer look at this table and its data types here because, on average, I'm only storing, my records are only, what, 100 bytes in size, even though, the min and the max are much, much larger values. So, maybe I can, pare some of this down here or something like that. So, now granted, sometimes because it's an average, you could have legitimate data in there that will blow out that average. But nonetheless, it's a good way to kind of just get an idea of things, or just at a quick glance, if you will. All right. So the next thing I want to show you guys is something called Set Statistics IO on. So when I am performance tuning, some people will say when they're performance tuning, oh, this is a crazy query because it returns 1 million records or 5 million records. I'm like, you know what? I don't care as much about the number of rows. I care about the number of data pages that a query returns because that tells me how much work it's really doing, right? And in order to get that information, we have to use Set Statistics IO. And you do it by doing this, Set Statistics IO on. So let's query a set of data. I'm just going to do a simple select top 50,000 from employee large and employee narrow. Okay. And then we're going to look at the messages pane here. And you can see here is that we did one scan, and then we did a bunch of logical reads. We didn't do any physical reads. The logical reads, the unit that's being expressed here is the number of data pages that we've processed. If it is a logical read, that means the data was already in the buffer pool, so we didn't have to read from disk. If the data was not in the buffer pool, then it would be serialized as physical reads. And you may see a mixed or match depending on what kind of data and what kind of work you're actually doing here. If we happen to have any lob records, those would also show up here as lob logical reads or physical reads. Read-ahead reads are also shown here too. That's another optimization that, depending on your data, you may be able to take advantage of that. What if we only queried a couple of columns though? Some of you guys may have seen that, oh, hey, you did a select star. Select star is bad, right? Well, what if I do just a select top first name and last name? I'm doing the same amount of work. Why? Because remember, we are reading data pages. So I still have to read those pages even though in the end I only want 2 columns of my entire table. So I'm still having to do the same amount of work. So some of you out there may be thinking, well, you don't have any indexes out there. Well, yeah, I don't. Neither of these tables have indexes on them, non-clustered indexes, I should say. So here's an optional little demo that I'm going to show you guys. So we're going to turn on actual execution plan. And I'm going to just do the select top 50,000 again against employee narrow. You see that we've done a clustered index scan, which is essentially a full table scan, right? And let's see, logical reads, 876. Remember that number. So now we're going to create a covering index that will cover this particular query up here. If you're not sure what a covering index is, essentially it's a non-clustered index that will fulfill a given query. That's a completely different topic and different session, but so unfortunately I cannot go further into what a covering index is here. And in this case, this simple non-clustered index is just an index, non-clustered index on first name and last name. All right. So let's do the same query again. Oh, hey, we did a heck of a lot less work, only 188 logical reads. because we did an index scan in this case. We went after our non-clustered index scan. Now, if you think about everything that I showed you guys earlier with the fixed var format, this non-clustered index only has 3 columns in it, technically 3, first name, last name, and the clustering key. It doesn't have everything else. So therefore, my record is much smaller. Therefore, I can shove more records into a data page, or in this case, an index data page. And that's why even though I did a full scan of this index, it did a lot less work because there's only those 3 columns present. All right, let's clean that up. Are you guys ready for your second dose of 400 level content? Here it comes. So we're going to be using something called DBCC page. This is technically an undocumented SQL Server feature, even though there's a heck of a lot of documentation floating around out there anyway that's unofficial. With this, we're actually going to be able to look at the internals of a data page. So, hold on to your seats. We're about to take a deep dive into SQL Server internals. So I'm going to use something called DBCC trace on. That's just going to print my output to the query window. Nothing terribly interesting there. I'm going to create a table called DBCC page example with string 1, which is a variable with data type, string 2, which is a fixed with char5, and then rec ID, which is an auto-incrementing integer. Notice that I intentionally put my variable with data types first, and then my fixed with data type second. And then we're just going to insert 2 sample values, sample string and foo, into string 1 and string 2. Nothing too exciting. Run that. Now, we're going to use something called DBCC IND to get internal information, allocation information about this particular table. In newer versions of SQL Server 2012 and beyond, you can use a DMF called sysdmdb database page allocations. I still kind of prefer the old way. Just call me stubborn, but this works for me. So we're going to run this against our page example. And what we see here are page IDs. We see page types. We see that this is in-row data. Page types, I have a little cheat sheet right here. Page type 10 is a IM page, or an index allocation map. But what we're really interested is in page type 1. It's a data page. Let's take the page ID, which is this value here, and then I'm going to plug that into DBCC page here. And then the file number is 1, and then the output type is 3. There's a couple of different output types. 3 is the most verbose, and 3 is the one that I'm going to be showing you today, and it's the one that I find the most useful. So if I execute that, I can now look at the internals of this data page. So first, if we scroll down a bit, we can see information that's stored within the page header. So DBCC page, makes all this, displays all of this in a nice, friendly format, if you will. But we can see, for example, if this particular table had multiple data pages, we'd see page pointers here for the previous and next page. Remember how I was talking about the record or the slot array? The slot count here shows us the number of records that happen to live on this particular data page, 1. We see that this is allocated. Now if we scroll further down, we actually see the hex that is our record. This is our actual first record that we just inserted in the fixed var format. Pretty cool stuff. And now because we're using DBCC page with its verbose output format, SQL Server or the DBCC page will actually show us the information about each of the different columns here. So rec ID is, remember, it was column 3 technically, and the value of 1, string 1, sample string, string 2, foo. It shows you the offset, which actually shows you where it is all up here. It's physical length 4, 13, and 5, because remember, for example, string 2 was a char 5, rec ID was an integer, so that's 4 bytes, etc., etc. Pretty cool stuff, huh? Well, if I were to take all of this, I can actually reverse engineer it into the fixed var format, and I did so in the cheat sheet here in the comments. So remember how we had status bits and the fixed length size and all this other stuff? So here it is, all completely broken down for you. Pretty cool stuff. I'm not going to go into this in detail, but just to show you that this can be done. The last cool little bit is that you can actually also take these hex values and using char and convert, you can reverse engineer the hex back to the original strings. Foo and sample string. Pretty cool stuff. Hey, I geek out on internals, so what can I say? So let me show you another example using the max data types. All right, so we're going to create a table called dbcc page max column with a varchar max, and then I'm just going to insert a short string value into that particular table. Okay, created that. Hey, remember sysdmdb index physical stats? Let's take a quick look at that for the dbcc page max column table. We see that there's only one page in this particular table and only one record. Okay, pretty simple and straightforward. So what I'm going to do is I'm going to use this replicate T-SQL to create a very, very, very long string. Just to show you, it's going to be a very long string, just repeated a bunch of times. That'll create a string that's 14,000 characters in length. Okay, and we're going to insert that value into dbcc page max as the second record. So rec ID 2. Inserted that. Let's take another look at our DMV of DB index physical stats. Oh, hey, we now have a second entry in here, one that shows that we have lob pages. We actually have 2 additional lob pages, even though we only have 2 records. What's going on here? Well, let's dive in deeper. Let's get the page information by using dbcc ind. Now we see that we have page type 3 entries here. What are those? If we go to our cheat sheet comments, those are text pages, aka lob pages. So that we see we have a couple of extra lob data pages, as we also saw from the DMV earlier. Let's take a look at our actual data page for the in-row data first. So if we scroll down a little bit, we see our first record, which was short string here, right? We see that it's a blob, but it's inline data, so it's represented on the in-row on the data page itself. Now if we go to the second record, rec ID 2, we see something completely different. These are our pointers. These are the pointers to the lob pages. In fact, I can grab either of these. These are the page IDs, so I can grab one of these, copy that, throw that into dbcc page, scroll on down, and hey, I see my very long string. It's all living in here. Here's all of our data. So what's the practical consequence of this? Well, let's take a look at statistics.io. We're just going to do a simple select. We're going to do 3 different select statements. One where rec ID is equal to 1, one where rec ID is equal to 2, and then one where we just pull everything back. Let's take a look at statistics.io. So in both cases, it shows us, oh, we only did 2 logical reads each. That's not bad, right? Scroll to the right, and oh, hey, wait a minute. Now we have lob logical reads, 5 and 6 in this particular case. We've had to do more work just to get that same data back because we wound up overflowing into extra pages. Now, that's not to say that, if you do need to store large string values, that's absolutely okay. You got to do what you got to do. But don't do this unnecessarily. Now, if I were to update that very first value again, I can just do that real fast. We see that if we use a dbc ind, we've allocated even more lob pages because we've taken that first value and changed that into a completely different lengthy string. We could look inside dbcc page, we would see the same thing again. And if we look at the consequences of IO, different long string, very long string, etc., it shows us we did 2 logical reads each, but in reality, we did 7, 6, and 13 logical reads on top of the 2. So it's extra overhead, extra work. All for 2 records. That's all it was, 2 rows. All right. Back to the slides. So I've talked a lot about internals and whatnot, so I'd like to pause for a moment and ask, Are there any questions up until this point? This is a good point to kind of pause for questions.
Andy, so far I haven't seen any.
Okay, I will give attendees about 10 seconds to throw any questions in that they may have.
Oh yes, that's one. Is there any reason to use non-varchar if you are not using international characteristics or
Is there any
business?
reason to not use nvarchar if you're not using international characteristics? Hold that thought. I have a slide on that later. So I will answer that later on. Next question.
Um,
Anyone else?
well,
Going on?
I
Yes, go
was
ahead.
wondering if what's the difference between the GUID and the varchar? Is there any difference in terms of storage space taken?
So the storage, let's see, I believe that is on the example slide for storage. Here we go. So unique identifier is also known as a GUID, and that is 16 bytes. So that's one reason why I generally favor auto-incrementing integers, which is only 4 bytes, or even a big int, which is 8 bytes, versus GUIDs, which are 16 bytes. But hold that thought. I talk a little bit more about clustering keys and GUIDs a little bit later.
Cool. Thank you.
Of course. All right. With that, let's keep moving on. Let me catch back up. Where were we? Transaction logging. All right. So you may be scratching your head. Why am I about to start talking about transaction logging? Well, I'd like to first throw out to you guys. Do you think that record size has an impact as to how much transaction log is written? Well, honestly, especially developers, they don't think about the transaction log. They don't care about the transaction log. That's an operational bit, right? Well, here's the thing. All insert, update, and delete statements all require writing to the transaction log. They all must be hardened to the transaction log. The consequence of that is that that's extra work that SQL Server has to do. And if you're writing code and you want your code to be, to perform as fast as possible, as efficiently as possible, you not only have to worry about what your code is doing, you have to worry about what SQL Server is doing. And that's why I like to talk a little bit about transaction log overhead. And if you're on the operational side of the fence, you know that the larger your transaction log, the more transaction log that gets generated has lots of consequences operationally. Not only does it have consequences with backups and restores, but things like replication, log shipping, availability groups. There's a lot of places where transaction log size and log volume have consequences. So does something as simple as your data type choices impact the transaction log? And the answer is yes. So with that, we go back to demo. And this will be a relatively short demo to show you transaction log overhead. So we're going to use set statistics IO on. We're going to use our database, every byte counts. We're going to take a look at sysdm tran database transaction. This is another DMV that I like. In fact, I'm going to highlight this right now. I'm going to use Control 3 and my typo. Whoops. Because I had the space in front of that, so I tried to use my SP help keyboard shortcut, but because I accidentally highlighted the space in front of that, it returned an error. But anyways, here's me using SP help, the keyboard shortcut that I showed you earlier. So we see that this is a system view. We see all the different records or data points that this DMV can show us. And for the purpose of our discussion, all we care about, all we're going to be making use of is database transaction log bytes used. So what this will show us is at this particular point in time, whenever you run this, how much transaction log has been written by a given transaction. So if I just do the select star from, we have nothing. And of course we have nothing. There are no open transactions currently running on my laptop. So what I'm going to do is I'm going to begin an explicit transaction. I'm going to do a select statement, and then I'm going to read from the DMV, and then I'm going to roll that transaction back. And in this case, transaction log bytes used is 0. Of course it's 0, because select statements do not write to the transaction log. We're going to follow the same methodology, and now I'm going to show you an update statement. We're going to do an update statement against employee large here, where last name is equal to Smith. We're going to roll it back, but before the rollback occurs, we still have to write to the transaction log. So we'll see how much transaction log gets written. 121,000 bytes. We're going to copy that value so that we remember that. Now we're going to run the same exact update statement against employee narrow. Remember, employee narrow and employee large are the same 250,000 records, right? Same underlying data. So let's begin our transaction and check how much transaction log is written to. 13,000 bytes. 13,000 versus 121,000 bytes. That's a heck of a lot less transaction log that I just had to write to harden this particular update statement. Again, it's all extra work that must be done. So if I can shave off and reduce that work, I've made that query that much more efficient. Let's do a simple example with a delete. We're going to delete records out of employee large where last name is equal to Abrams. 155,000 bytes of transaction log, and then delete against employee narrow. 24,000 bytes of transaction log versus 155. That's a huge, huge, huge difference. And again, don't think of this in the context of just one single query. This is just one demo query. Think of this in a highly transactional environment. Pretend that you have queries that are running, hundreds of queries, thousands of queries that are running every single minute, pounding on your SQL Server. And you have lots of DML that's going on. All of this is hammering your SQL Server. All of this is writing to transaction log. All of this adds up, and it adds up fast. So if you want something that performs and scales really well, you want to minimize as much work as possible. And again, just by making simple data type choices, or good data type choices, you can help to minimize that and mitigate some of that performance overhead. Or if you're careless and you make some poor data type choices, you're gonna pay the price. You're gonna pay the piper later on down the line. That is the end of that demo. That was a nice short demo. So I talked about that so that I can talk more about this, the next topic, page splitting. So what we have here is a visualized version of a clustered index. Okay, the blue represents different records here. Let's pretend that we are clustered by last name, just for simple simplicity's sake. And now we have to insert a record where last name is equal to Matthews. It's something that's in the middle of the alphabet, so it has to go into the middle of our sequence. Well, as you can see, the data page that Matthews needs to be inserted into is quite full. So what does SQL Server do? It has to do something called page split. So what SQL Server does is when it's forced to page split, it will take approximately half the records that are on that particular data page, it will allocate a new data page somewhere else, it'll copy that data over, and then it'll reattempt your insert. If, however, your insert, the value that you're inserting, the record that you're inserting, is so large that you can't fit it into this new half-split data page, SQL Server will split again. You can have cascading page splits, and these are really, really, really nasty. There's a lot of overhead with page splits. Page splits can't always be avoided, but they can be mitigated. We want to try and reduce them as much as possible. We don't want to have unnecessary page splitting because of their cost, because of their expense. Now, page splits only occur on cluster tables and they only occur on insert operations. Well, what about a heap? Well, a heap is an unordered set of data, right? So what SQL Server will do is that it'll just scan all of the data pages until it finds a data page that happens to have enough space to fit your record, and then it'll insert that. So if you happen to have a very large heap that's, thousands, thousands, or hundreds of thousands of data pages, it's got to do essentially full table scans in order to do a singleton insert or your singleton inserts. That's one of the reasons why, in many cases, heaps are not a good scenario if you're doing a lot of singleton insert operations, as opposed to bulk inserts, which are a different topic. Well, what about an update on a variable length column? Well, interestingly enough, what will happen with an update is that SQL Server will attempt to will attempt to expand the row if as it sits on that particular data page, or it'll try and move that row somewhere else on that data page. If it doesn't have enough room, it will actually change that update into a delete and an insert operation. And then that insert operation then will force your page split. Another interesting detail to note about page splits is that, say for example, we're part of a transaction, right? And then we do this massive insert statement that causes a bunch of page splitting, and then later on down the line, somewhere in that transaction, something causes a rollback. Do you think all these page splits are rolled back? The answer is no. Page splits are never rolled back. In fact, page splits, when a page split is occurring, will actually be executed within its own system transaction. It's something that cannot be stopped, if you will. So let's take a closer look at page splitting and some of the consequences of page splitting in another demo. All right. Thank you to Paul Randall for his inspiration and for this particular demo. I'm using some of his techniques in here with permission, of course, and credit. Okay, so first we're going to create a simple table called single data page. That's just going to have a rec ID with an integer, auto-incrementing integer, and then one column, my value, that's a char 1000. I'm intentionally doing this just to blow out the table size. And then we're going to insert 6 records. The values 1, 2, and 3, 5, 6, and 7. So we're skipping 4. We're going to also take a look at sysdm db index physical stats again afterwards, so that I can prove to you exactly how this table is set up. So we've executed, set it up. So we have 1 page and 6 records. Okay? So what we're going to do here is that we're going to begin a transaction, and we're going to follow the same methodology throughout much of the rest of this demo, is that we're going to begin a transaction. In this case, I'm going to insert 1 record at the end of our sequence, the value 8. We're going to take a look at sysdm database transactions, and then we're going to commit the transaction. And then we're going to look at our DMV, the DMDB index physical stats once more. Okay? See what has changed internally. We'll execute that. We see that for transaction log that's been written, only 1,244 bytes have been written. Not very much. That's really good. But we see that no page splits have occurred because we only still have 1 page here. All right? So now we're going to do an insert. We're going to insert 1 single value into the middle of our clustering key sequence. We're going to insert the value 4, and then we're going to follow the same methodology as before. Now we see page splits have occurred. If we look down here at the output of our DMDB index physical stats, we actually see that we have 2 pages here on the leaf level, and then on the root level we have one other page up here because we had to expand the B tree. And if we compare the amount of transaction log that was written, 1,200 bytes versus 7,100 bytes, a heck of a lot more transaction log had to be written because we had to do these page splits. That's pretty expensive, just because we inserted 1 record. It's a lot of extra behind-the-scenes overhead. So let's take a look at a skewed example, a skewed distribution example. So I'm going to create a table called integer cross-reference table, or xref table. You know, we all have tables like this where we have a bunch of different keys. So there are essentially 5 integers in here, okay? And I'm just going to be inserting a bunch of random values into those integers. But for the clustering key, which is rec ID, I'm going to insert only 1 record with the value of 1 and 217 records with the value of 3. And by the way, some of you guys may have never seen this before, but what am I doing here with this go followed by a number? It's a cool little shortcut where if you have the batch separator go followed by a number, what SQL Server will do is that it will loop and repeat everything in that particular batch that many times. So I didn't have to write a loop here. I didn't have to write a cursor here. I just had to do go 217. I would not recommend using this in production code, but on the other hand, it's great for things like demos or if you're just doing a mock or a test of some sort. So let's set all that up, and we'll take a look at our DMF afterwards. By the way, if I look at the messages pane, you see batch execution completed 217 times. I did this operation 217 times. Pretty cool little trick, a little shortcut. All right, so integer cross-reference table only has one page with 218 records. Remember, it's one record with the clustering key value of 1 and 217 records with the clustering key value of 3. Okay? So now what we're going to do is that we're going to insert one record with the clustering key value of 2 into this table. And remember, this is a completely unbalanced table here, right? Let's see what happens. We're going to follow the same methodology as earlier. We only wrote 260 bytes of transaction log. That's not terribly much. That's really good. But in this case, we did not page split at all. No problem. Let's do it again. And let's see what happens. Whoa! 10,000 bytes of transaction log were written, as opposed to 260, all because I had to page split. This skewed example shows that the page splitting is not a linear price, if you will. Depending on the distribution of your data, a cost of a page split from a transaction log perspective could be really, really, really nasty. And in this case, it is. It's a huge, 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 huge increase. So some of you may have been sitting there wondering to yourselves, why is Andy talking about this? This is a data type session, right? Well, you know, I mean, this may be cool and all, but what does this have to do with data type choices? Here's why. Clustering keys. How many people here have developers who like to use GUIDs as their clustering key? I've dealt with many developers who love GUIDs, and GUIDs are great on the application side of the fence. But here's the thing. They are terrible, absolutely terrible, as a SQL Server clustering key. And that is a poor data type choice. So let's talk about that. So I'm going to do a little bit of cleanup. And then we're going to take a look at, let's see, we're going to record some information out of employee large from DMDB Index Physical Stats. I'm going to record the total number of pages on the leaf level. I'm also going to record the total number of pages on the intermediate level here. Okay. Now what we're going to be doing is that we're going to be inserting records into employee large. We're going to be using new ID. And remember that new ID generates a brand new random GUID. Let me remind you by using my keyboard shortcut that employee large happens to be clustered. Employee ID is a unique identifier, and it happens to be clustered on employee ID. Okay. So we're going to be inserting one record at a time. We're going to be looking at the transaction log bytes used, and then we'll be looking at index physical stats. All right. And we're going to have to do this a bunch of different times because every single run will have a potentially different result given the randomness of new ID. Okay. First time, 11,000 bytes have been written. We've increased the page count, so we see that 2 page splits have occurred, one on the intermediate level, one on the leaf level. Oops, I unhighlighted that on accident. So let's repeat, keep going. 12,000 bytes, we have 2 page splits again. 13,000, 14,000, 14 again. Eventually we'll hit a case where we either only have 1 page split or we have no page splits. Eventually that happens. Only 7,000 bytes of transaction log were written, and in this case we only had 1 page split occur, not 2 page splits. I'm not going to keep going with this, but eventually you'll see an example where no page splits actually occur, and that, if I recall correctly, the amount of transaction log bytes written is around 3,000 or so. So it's a heck of a huge difference. And here's the thing. This is happening with almost every single insert. We're page splitting like crazy here because our developers wanted to use GUIDs as the clustering key. Boo! A lot of extra unnecessary overhead for our SQL Server that makes SQL Server sad. So I want to share some thoughts on the GUID clustering keys. I subscribe to the school of thought following Kimberly Tripp of SQL Skills that a good choice for a clustering key or good guidelines for a clustering key that should meet 4 criteria. It should be narrow, unique, static, and ever increasing. I'm not going to go into great detail about these 4. Kimberly talks a lot about them on her blog, which I'll have a reference to shortly. So one of the things is about these, though, is that a auto-incrementing integer or big integer happens to fit or happens to fit all four of these criteria. It is much more narrow at 4 or 8 bytes versus 16 bytes of a GUID. It's unique. You can only have 1, 2, 3, 4, 5, whatever, because it's auto-incrementing. It's static because it's a value that never changes, and it's ever increasing. So what about using new sequential ID? A lot of people like the idea of new sequential ID. What new sequential ID does is that it will give you a new GUID in order. Here's the thing, though. What value does it start with? Well, that starting value is reset every single time not SQL Server is restarted, but the underlying Windows server is restarted. Because new sequential ID, all it is a call out to the Windows layer, to the Windows API, to get another GUID. So every single time you reset your Windows server, and I hope you do, because I hope you're doing, if nothing else, I hope you're patching your servers on a regular basis, your new starting value, your next new sequential ID, could be anywhere on the spectrum. So in a sense, you're kind of playing roulette here. So think of it as, say, a number line. So let's pretend that new sequential ID instead are numbers just for visualization purposes. So you start at 50,000 and 51, 52, 53, 54,000, blah, 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 blah. You reboot your SQL server and your Windows server. Next time around, that new value could be 1. It could be 1 million. So it could be something further on, or it could be something less. It could be something right in the middle of your existing sequence, which will at which point you're going to be in page splitting hell, essentially. So you could use new sequential ID, but you have to understand your workload and that there is an underlying risk. Now, the probability of collisions are minimal. The probability of GUIDs starting beforehand or afterhand, it may or may not happen, but again, you have to know your workload and how you guys maintain your servers. So the guideline that I often like to give to developers who want to use GUIDs, because again, GUIDs are very useful on the application layer, is to separate the idea of the clustering key and the primary key. Think of the primary key as your business key or your application key, and think of the clustering key, if necessary, as an internal SQL Server only value. So what I would like to do, especially if my developers are really insistent on having GUIDs, is that I say, fine, I want this table to be clustered on an auto-incrementing integer, and then I will set up a non-clustered primary key constraint on your GUID. So therefore, your GUID is still supported, but then I don't have to incur the cost, the extra overhead of unnecessary page splits. Again, you can read a lot more about clustering keys and GUIDs, et cetera, just by simply Googling Kimberly Tripp off of SQLskills.com or go to that URL. She's got a lot of content written about this particular topic. So I've talked a lot about schema. I've talked a lot about internals. I haven't talked so much about T-SQL, and that's what this final chapter is about, implicit conversions. Let's talk a little bit about that. Alike or not alike? Well, if we look at these values, to us, variable 1 and variable 2 and the underlying values, they're the same, right? 5 is equal to 5. This is a string is equal to this is a string. However, to SQL Server, if depending on the data type choices, they may not be alike. And in this particular case, or this particular example, because the data type choices all differ, they are not alike at all. SQL Server can't compare and contrast these directly. It has problems. What does SQL Server do? It must convert using something called the data type precedence chart. So what happens is that SQL Server takes the smaller of the two values as far as the data type precedence chart is confirmed, and then it upconverts that value. So if you're comparing a big int and a small int, whatever that small int is, it's converted implicitly to a big int, and then the two can be compared against one another. And this has a cost. And let's take a look at that cost in T-SQL code. Implicit conversions, our final demo. All right, going to turn setStatistics.io on. We have to turn on actual execution plan. So I'm just going to do a simple query here where I'm going to do a select where I have my small int and my big int. And I'm just going to match my small int is equal to my small int. And then another one where my small int is equal to my big int. Okay, let's take a quick look at that. I'm going to expand this out. Now if we take a look at the execution plan, in this particular case we have to look at the filter operator. So let's take a look at the first filter operator. I'm going to use zoom it. In this case, startup expression predicate, my small int is equal to my small int. No problems, we're good here. However, if I go to the other query, go to the filter operation, oh hey, look here, we have something called convert implicit, where my small int has been converted to a big int, and then it can be compared to my big int variable. If we actually look at the query costs, in this particular case, the estimated subtree cost is blah, blah, blah 17 versus 18. A trivial difference, but it is just a hair of a difference here. Now, granted, these two queries are extremely simple, but the cost can add up. Now, what if we have varchar and nvarchar? Okay, so first we're going to look at varchar is equal to varchar, and then nvarchar is equal to varchar. Look at the filter operator of the first. Nothing here because varchar is equal to varchar. We look at the second filter operator. And again, we have another convert implicit operation here. The varchar had to be converted to an nvarchar. Well, let's create a quick covering index on employee narrow, just last name, employee ID, and we're going to write some queries against that using this non-clustered index. So what I'm going to do now is that, oh, and by the way, what was the underlying data type of employee narrow? Because we're going to run a query against it where last name is equal to last name matching. Last name matching is defined as a varchar 100. I forgot what employee narrow was. Do you guys remember? I don't. So I'm going to use SP help again to double check. Varchar 100. All right, hey, we match up. That's great. So let's take a look at this. We execute that query, look at the execution plan. Now we have a nice index seek. That's really cool. Nice, fast, efficient. If we look at the messages pane, 3 logical reads. We had to look at three data pages. That's really cool. Hardly any work. That's fantastic. That's what we normally want to see because we matched our data types. Now, what if we query with a larger data type? Let's say we were lazy and we just set up last name as an nvarchar 100, not as a varchar 100. What do you think will happen here? If we look at the execution plan, we see that SQL Server is actually forced to do an index scan, not a seek. If we look at and hover over the index scan, we see that we have a convert implicit that has occurred here. So what happens is that, remember, the smaller of the two data types must be up converted to match the bigger one. Which one was a smaller one in this case? The varchar 100, which is a column on the table. So what SQL Server has to do is it must scan the index, scan through every single value, up convert every single value, all 250,000 values, and then it can compare it against your variable of last name and varchar. So I had to do a heck of a lot more work. Let's look at the messages pane. I had to do 1,000 logical reads as opposed to 3. A heck of a lot more work just because I mismatched my data types. What if we query with a smaller data type? Let's use a char 5 here. Oh, hey, we have an index seek here. We only did 3 logical reads. Why is that? Now, there's one little trick when it comes to strings. Char and varchar conversions are free. Nchar and nvarchar conversions are free. So you can compare a varchar 50 and a varchar 150 against each other, and that conversion is actually free. You don't have to pay the implicit conversion penalty. So you may actually be dodging a bullet here if a lot of your code is just using a bunch of different varchar values of different lengths. Well, you know what? Again, because the conversions are free, you may not have noticed that extra overhead, or you've avoided that extra overhead, I should say. Here's a quick example of comparing with a larger free data type of a varchar 500 versus the varchar 100. And again, we see that we're able to do an index seek, and we see that we only have 3 logical reads. Finally, let's query with a max data type. I'm going to set last name char as a varchar max. Okay. We see in the execution plan that we actually had to do a couple of different other physical operators here. SQL Server had to do something completely different. It couldn't do a direct index seek. It had to do a couple extra operations here along with a nested loop. In the end, though, it still wound up being 3 logical reads, but nonetheless, if you have a much more complex query and a lot more complex things that are going on, that can really screw with your potential execution plan. So that's one reason why people say, well, why can't I just use varchar max in all of my store procedure codes? Who cares? Because the conversion is free. Not quite. So that brings us to the end of that demo. Now, finding implicit conversions. Now, no one wants to sit through all their code or manually run it and look at the execution plans in order to find implicit conversions. Thankfully, Jonathan Cahias of SQL Skills has done the work for you. He has actually written a bunch of code that will go out to your plan cache, read the contents of your plan cache, and return back to you queries that have implicit conversions in them. So you can actually go run his code right now, hopefully against a QA environment or a staging environment, not production, and actually find code from your applications that are incurring this extra overhead of implicit conversions. So you can go digging for that immediately. Thank Jonathan Cahias for the awesome work that he did with that. To Unicode or to not Unicode. So someone earlier had asked about, who cares if we're not using internationalized characters or things like that? Do I ever need to use nvarchar if I'm not using internationalized characters? So for the longest time, I was of the mindset of, if you know your application is not using internationalized characters and you don't need that, don't bother with, any of the N data types, right? And that resulted in this little tweet here a number of months back. And the subsequent conversation I had with a number of individuals, including Aaron Bertrand, kind of opened my eyes to some of the possible consequences. So what I'd like to do is present some pros and cons. Because here's the thing, in SQL Server, just about everything we do is a trade-off, right? So if you err on the side of just using varchar, data could be lost. What do I mean by data could be lost? Well, have you ever had a situation where you have your application and suddenly your sales team comes to you and says, hey, we're going to be demoing this to a Chinese client tomorrow. We're going to be going international now. Have you changed all your stuff to support all that? Well, too late. We've already demoed it or we've already sold it to this, international client. I hope it's ready to go. Good luck. Well, yeah. So if you actually try to store in, Chinese characters in a varchar, boom, it's gone. And if your application doesn't have proper error handling, because that's something that you never dealt with before, boom, that's gone. You may not even trap it. You may not even know that's happening. And, by that point in time, your application has probably been around for a while. And refactoring your application could be a huge undertaking. It could be extremely painful. So that's a potential trade-off. That's a potential negative cost that you may have to pay down the road, but may have to pay it. Who knows? On the other hand, if you err on the side of always using a Unicode supported data type, using one of the N's, as I like to say, well, your storage and your I/O requirement will be doubled. So if you're if you're lucky enough to be in a large enterprise that happens to have, say, massive servers with terabytes of RAM and whatnot, that's great. But if you're in a small shop that's still stuck using a standard edition where you have RAM limitations and you're still trying to run fairly hefty workloads, and you're constrained, well, you're going to pay that price immediately here. So is that a price that you want to pay? The point to all this is that you need to be aware of the trade-offs and of the consequences, such that if you choose to err on one side or the other, that there will be a price to pay regardless down the road. And like I said, everything is a trade-off, right? So, but be conscious of which of the consequences of the choice that you make. And interestingly enough, after before the conversations I had, when I said this tweet, I was always of the always use a varchar mindset. But afterwards, I'm more open to the end data types and defaulting to using the end data types because, yeah, some of my colleagues made some very good points, and so I'm definitely much more open to the other side or that second approach. So I want to share some parting thoughts. Right size your data types. Please, please, please take the time to right size your data types. Hopefully I've been able to demonstrate and show to you guys why this is important and some of the cost and overhead of poorly sized data types. Be mindful of the 8 kilobyte data page limit and the consequences that it has on I/O and the work that you're making SQL Server do with your queries. Please, please, please match your data types. Implicit conversions can be a real killer, and you know what? Matching your data types, it's not that hard. It just requires an extra little bit of effort. And if you use SB help, that keyboard shortcut all the time, as I like to do, you can match your data types very, very quickly, very easily. And as you're dealing with code and whatnot, at least be mindful of internals related performance impacts. There's a lot more going on with SQL Server, and if we want to have SQL Server be as lean and mean as possible, it's in our best interest to be as mindful of all the different impacts our code and all the different choices that we're making have on SQL Server. So with that, before I stop for questions, I want to show you guys one last little bonus. So as many of you have heard, and one of your future speakers will be talking about, is SQL Server vNext. In production or in the wild right now, we have SQL Server 2016. SQL Server vNext is coming on down the line, right? It's currently in CTP, a Community Tech Preview. In fact, just the other day, CTP 1.3 was released, right? Well, check this out. So I am actually, if any of you were savvy enough to notice, I'm actually running CTP 1.2 right now. But here's my extra bonus version. Yeah, vNext CTP 1.2. Pretty cool, huh? On Linux. Everything you have seen here today is SQL Server running on Linux on my laptop. And all of the things that I've showed you today, all the internals, are all identical, regardless of whether you're running SQL Server on Linux or SQL Server on Windows. So that's my little bonus to you guys, just something that I think is really cool, that yes, SQL Server for Linux is, in many regards, almost ready for prime time. It's really cool. I love it. I used to be a former Linux guy myself, so that's why I'm super, super excited about this. All right, so thank you very much. Are there any final questions?
Yeah, we got several questions here. Andy, this one was saying, this was asking, I've noticed a tendency for DBAs to use Wildcard 255 instead of CAR almost universally. The reason they give is that they don't want to have to alter the table when the business decides to store longer values in a text column, as that would require manual work. Instead, they choose to run records reorgs every weekend to compensate for the page split due to the update statements that store large values. In those large values in those same columns, these reorgs are automated, of course, so no manual intervention is required. Is their argument valid?
Is their argument valid? Is their approach valid? Well, as I kind of said earlier, everything that you choose to do in SQL Server, I believe, is a trade-off. So if you want to kind of be somewhat sloppy and use varchar 255 everywhere, of all the different things that you could be doing, that's not so terribly bad, as long as you, again, hopefully also matching your data types underlying within your code that's using it. Um, so that being said, yeah, to me, it strikes me as kind of lazy development or lazy modeling, but is it one of the worst sins you can commit? No. So again, it's a trade-off, but at least be conscious of the trade-offs. I'd be far more concerned about implicit conversions and sloppy data type matching from that perspective than anything else. But yeah, again, it's it just strikes me as people who don't want to do the right thing now, but will it kill you in the end? Probably not. Probably, but as I said in the Unicode versus non-Unicode, it may also burn you later on down the road. So, you know.
Cool.
Any other questions?
Yeah, another one is do insert commands run faster on a heap uh, table versus one with a cluster index?
So, of course, the answer is it depends. So, generally speaking, there are some cases where bulk insert operations work very, very well against heaps. Um, these are the types of operations where you're dumping in massive amounts of data in one single insert batch statement, as opposed to singleton inserts. Singleton inserts are terrible against heaps because remember, as I was talking about in the page splitting slide, SQL Server for each individual insert must scan the entire heap in order to find a data page that happens to have enough space. As opposed to with a clustered index, SQL Server, depending on what the clustering key value is, knows exactly where that record or those sets of records must be inserted into. And if you're using an auto-incrementing type value as your clustering key, it knows exactly where it needs to go, right at the end. So that's kind of the general guideline. But honestly, there are very, very few cases where heaps are superior to clustered indexes.
Cool. And another one is what about package database like CRM? We will have no way of alter the data type, correct?
I'm sorry, yes, unless you want to try and break your vendor application, but unfortunately with vendor applications, yeah, you're kind of trapped, unfortunately. So it is what it is. When dealing with vendor applications, you have my sympathies.
Also, she wanted to know when will the SQL v.next to be released to general.
I do not have that information. I do not know anyone who has that information outside of Microsoft, and I don't even know if Microsoft has that information as of yet. So again, they're in the community tech preview cycle. Once they are, with each SQL Server release, they will go through community tech previews, and then they will go through release candidates. So we haven't even hit release candidates yet. Generally speaking, historically, we'll usually see 1-3 release candidates. So it would not surprise me if we see it by late next year, but don't quote me on that. Microsoft has been moving to a much, much faster cadence when it comes to SQL Server development, and especially what's really helping this out is Azure. Because a lot of the code that you're seeing in, say, SQL Server 16 before SQL Server 16 went live has been live in Azure for years. Query Store, which is a brand new feature in SQL Server 2016, has been in Azure in one form or another for almost 2 years now. Or so they're using Azure as a test bed for a lot of things that will eventually trickle down to us using SQL Server, the traditional releases. But the benefit of that is that we are seeing new versions of SQL Server come out much, much, much faster. So, but as to an actual date, I haven't the foggiest idea.
um, there's one part that you were saying the record, if the record cannot be updated, then SQL Server has to do delete then insert.
Yes, that's correct. When you're attempting to update a variable length record and that record on the data page does not have enough space to support the new size of that record, it will then implicitly convert that into a delete and insert.
So that only happens when it's too large?
That's correct.
Okay. Um, also, yeah, Amanda is asking if the V.Next connect to Power BI reporting.
My guess is yes, but to be honest, I don't do very much in the BI realm. So if I recall correctly, Steve Wake next month, I will definitely be able to answer that question for you. Ask him.
Cool.
I'll be honest, I've never even touched Power BI. Have sat in a couple of sessions in the past just to check it out. I'm like, oh, this is really cool, but I have no personal use for it, so I've never checked it out. So
Cool. When you mentioned the GUID, like not to use it as a clustering key, so you would think, I guess in your opinion, you may want to use, you want to suggest to use a surrogate key as the clustering key, right?
that is correct. That's my general guideline. Again, you may have specific situations where you may want to use a GUID as your clustering key, but again, I'm speaking in generalities here.
Okay. So would you say you prefer not to use a GUID as even primary key?
Like I said, that's the kind of compromise, if necessary, uh, if your application developers really want to have GUIDs and whatnot. So then I'll say, yeah, that's fine. Use it as a non-clustered primary key, and then I'll have my clustering key be, the auto-incrementing integer or big int. That's a compromise that I often find works very well for my developers and the cases that I've encountered.
Sounds good.
All right, anything else?
Okay, there's one more. Uh, may there be any impact of choices of data type in relation to in-memory OLAP, OLTP?
So my presumption is yes. Unfortunately, have not been able to deep dive and really explore and learn Hackathon, or in memory, I should say. Um, Kaylin Delaney has done some fantastic writing about um, in-memory internals. So it's on my list of things that I need to read, but that list of things is pretty freaking long. That being said, I would assume that it has impact. There's no reason why it wouldn't, because I mean, everything in the end, everything boils down to storage of some sort and processing. SQL Server has to crunch through bytes, regardless of whether it lives on disk or lives in memory. So the same general principles I imagine will carry on over to wanting to maximize and right-size your data types. So I don't see why we would not have similar kinds of impacts in a hackathon type scenario.
Cool. And so somebody wants to know if the code will be made available for.
So older versions of this presentation are already available on different SQL Saturday websites because I've been presenting this for quite a while now. The only version that is not currently available is the one that I've just showed to you here because I made some improvements for the past summit. And really the only new thing that's in the demos in the past summit version are the DBCC page demos. All the other demos are already available. So again, just go search under my name, SQLSaturday.com. Every byte counts. You'll find it really fast.
Cool. Thank you.
Of course. Any other questions?
Let me see.
Going once, going twice? Come on, guys.
Oh, I just remembered. Yeah,
Yes,
I have a quick question. When you say like in your demo, the comparison between small integer um, versus the big int, it's like a implicit uh, conversion before you do
correct.
the. Um, Well, in that situation, what would you do? I mean, the table already set up that like that way. Um, do you have to convert your columns into same kind of the data type, or what would you suggest?
Well, I would suggest matching your data types because otherwise, again, it's going to happen implicitly in your code. I mean, if it's going to happen in some way, shape, or form, regardless. So the question that you have to ask yourself is this: how often are you querying that data? How often are you making those comparisons? Are you making them frequently? Is this one of the, say, top 100 queries that your application fires hundreds of times a minute? Or is this something that's reporting that maybe runs once a month? All right, fine, who cares? You know what I mean? You don't care about its performance. But again, it's all about trade-offs. Is it worth the hassle versus the hassle of refactoring your table schema, or is this a trade-off that a performance trade-off that you can live with? That's what you have to ask yourself, but at least be conscious of the consequence. So I can't give you a guideline. You have to ask yourself that question for each individual scenario.
Yeah, that's right. Any more questions, ladies and gentlemen? I don't see any more questions. Just a second. I see this person raised hand. Uh, just a second.
Sure.
Uh, the Gwen. Hey, I saw you raise your hand. Do you have a question or anything? Gwen L. Okay, no. I guess that's it.
All right. Well, thank you very much for having me. This has been a lot of fun. I really hope you guys enjoyed yourselves today. I had a good time. So yes, thank you again for having me. This has been great. I hope you guys got something out of this.
Thank you so much, Andy. I've learned this is the second time I listened to your presentation, but I still learned a lot from it. Thank you so much for spending the time and present for our virtual chapter.
The pleasure has been all mine. Thank you very much. So
Okay, thank you, Andy.
Right. This is a great presentation. Thank you. Thank you, everybody, for attending. Goodbye, and see you. Hopefully, to see you next month.
Bye.
good night.
Good
Good
night.
night.